Okay, so we talked yesterday about indefinite integrals. Another form of an integral is referred to as a definite integral. And really, we looked at that during the first 2 weeks of this course, where we were looking at area underneath the curve, because a definite integral represents area underneath of a curve. So if you are looking for your area underneath of a curve of what we're looking at down here, you could write that as a definite integral from a to b of your function dx. So a lot of this is the same as an indefinite integral that we looked at yesterday, except we have bounds, the a and the b here. But more in the context of what we want to focus on today is basically related to what we did beginning of the course, where we were approximating the area underneath of our curve by doing rectangles and doing more and more rectangles. The rectangles here are considered to be inscribed because all these rectangles are below. Notice, to begin with here, our left endpoint rectangles are inscribed because they're below. But then from here over, it's our right endpoint rectangles that are inscribed. So when we were beginning of the course, it was always either just the left or just the right that were below. And then over here, these are circumscribed because all these rectangles go above and include a little bit extra. But for the most part, to be able to find your area, you can still look at your inscribed, which would, if we look at x squared, which you know is your parabola, and if we're only looking to the right of our origin, these would be our inscribed here, these would be our circumscribed here. Inscribed always include, or forget to include, a little bit of a triangle here at the top. It's not technically a triangle, but it's fairly close to that. Our circumscribed always include a little bit extra, go above and beyond the curve. However, this part that's above and this part that's below that we're missing is referred to as the error. But to reduce your error, you can always increase the number of rectangles. And the more rectangles you do, the smaller your error gets and the closer you get to the actual value. In other words, the number of rectangles that we're dealing with goes off towards infinity. Now, just to review, from what we did beginning of the course, if we were looking for the area underneath our x squared from 0 to 3, we could use our program from our CPM, the beginning. So you'd want to put x squared into your y equals, and then you'd want to use your program. You'd have to enter your beginning, which would be 0. You'd have to enter your end, which was 3. And in this case, you're asked to do 10 rectangles, so the number of rectangles or number of pieces would be 10, and your calculator program should spit out these numbers. If it doesn't, talk to me in class so we can figure out what it is you're doing wrong, whether it's your program or whether you entered something wrong. Now, we're going to look at ways today to be able to find the exact area. But for the most part, it starts out with summation notation, which we looked at in Algebra 2 some. And so we're going to take a couple problems to refresh what's going on here. So summation notation, this funny looking E means you're summing up all these terms. So to find your first term, you take k being 1 and plug it into your rule. This is the rule. 1 plus 1, you know, is 2. This funny looking E means summation notation, so then you have to go plus, and then you put in the next number up. And these numbers that we're putting in are always integers. We just put in 1, so the next number up from 1 is 2. Plug 2 in here, 2 plus 1 is 3. Then you go plus, plug in the next number, take 3, plug it in, and you get 4. And you keep doing that until you plug in this top number. Once you plug this top number into here, then you stop. And so in that case, it would be 8. So what we have right here would be your expanded form. which if you wanted, you could go ahead and add these together, and in this case, you would get 35. On this problem over here, our rule is 2 to that power. So we got to start out by plugging in 1, we get 2 to the first. Then we go plus because it's a summation, which means we got to add. Plug in the next number up from 1, which is 2, we get 2 squared, which we know is 4. Plug in the next number up from 2, because we just plugged that in, would be plugging in 3. Plug 3 into your rule, and you get 2 to the third, which you would know is 8. And you keep doing that until you actually plug in this top number. When you plug in that top number, plugging in a 2 to the sixth, that's what you would stop with. Now you could either do this in your head or work it out with your calculator, and you would get 126. For the sake of working out some of these problems that we're going to be doing, these are some summation rules or formulas. Now, for the most part, if you know the value of n, you want to use this first rule. If you don't know the value of n, so if n is going off towards infinity, then you want to use the second rule. So if you don't know the value of n, or the value of n is going off towards infinity, you always want to use the second rule. If you do know the value of n, you use the first rule. Also over here, if you're multiplying your number times a variable, you can put that number in front and then just deal with this. Here, basically it's saying you can distribute your summation through, or here, sum of 1 basically would be 1 added together n times, or 1 added n times is just n. That's what this one is saying. If you have the sum of I, which would be very similar to what we were dealing with here, it's just what we have here in these two formulas. Or the sum of I squared would be these two formulas, or the sum of I cubed would be the bottom two formulas. So looking here, the first thing I'm going to do is basically distribute my summation through to each part. So I'm going to take the sum of 7i squared minus the sum of the 5i. Because we are multiplying a number times your variable here, we can go ahead and take and put that number in front. Then we're going to go I, or 7. Now we have the sum of an I squared. So we're going to look at I squared, which is here. Once again, we know the value of n for this problem, so we're going to use the first formula. And so n would be 10. You plug a 10 here, here, and here. So in other words, we get 7 times 10 times 11 times 21. Now, for the second part, we're dealing with the sum of I. Sum of I, well, that's right here. We know the value of n once again, so that means we're going to be dealing with the first one. N would be 10, so we'd go 10, and then 10 plus 1. And so we get 5 times 10 times 11 over 2. So we can work this out on our calculator, and we would get 2,420. So with this problem here, we need to take our limit of all this. But you notice the top is really a sum. It's a sum of 1, 2, 3, 4, 5, 6. In other words, if you write it as summation notation, it's really just the sum of all those numbers added together. So it's the sum of I. Well, we do have a formula from the previous page for the sum of I. So, and by the way, we don't know the value of n, so I'm going to use that second one. So that's the one that's written as separate fractions. Now, We could either take this n squared on the bottom and bring it up as an n negative exponent, so we'd have the whole top multiplied by an n to the negative 2 distribute through, or you could take and write this as separate fractions. 1/2 n squared over n squared plus 1/2 n over n squared. Either method works, does not make a difference. And I'm not sure what that's about there. Sorry about that. And then we need to go ahead, we simplify the first fraction, the n squareds drop, we just have a half plus here, there's one more n on the bottom, so it's really 1 over 2n. Now it's a lot easier to take your limit as n approaches infinity. As n approaches infinity, it has no effect on this because there's no n's. N approaches infinity here, you're plugging in big numbers on the bottom. 1 over something really big is close to 0, so it's just 1/2 plus 0, so your limit would be 1/2. So basically, getting a review on that summation notation, we can now go ahead and take a look at finding area. Now, each rectangle here, how wide it is, basically, if your interval is from A to B and you're dividing it into n pieces, you take the total length or width of your interval, which would be your B minus A, the big value minus the small value, divided by the number of pieces. If you are looking for your area underneath the curve, that would be all your inscribed ones. And notice it's got the bar underneath, so you know that's underneath your curve. You would have this right here. If you're looking at your area above the curve, that would always include a little bit extra, and that's why we have a bar above. Well, if you go ahead and do either one of these, you would know that your actual area would be somewhere in between. Now, we can get to that area basically as we let the number of rectangles go towards infinity. So n goes towards infinity. So for the most part, we're going to take a look at our doing a sum of all these rectangles, and then we're going to take the limit as n goes into infinity. The number of rectangles goes to infinity. And that's what we're saying here right above the box. Now, the two formulas that are going to be very helpful is basically finding delta x, which once again is total width, b minus a, divided by the number of pieces. And then x sub I, what we're plugging into our function, which is x sub 0, the beginning, plus I times delta x that we just figured out here. Notice it says very important, and it's boxed in a big red box. Make sure you have these highlighted or something like that, because we're going to have to be using these formulas. So let's go ahead and try to work out the exact answer for the area underneath your curve of y is equal to x squared going from 0 to 3. Well, here's our two key formulas that we're supposed to be dealing with. B is the end of your interval. A is the beginning of your interval. So you're going to get 3 minus 0 over n. In other words, we end up getting just plain old normal 3 over n. Now, x sub I, what we have to put into our function is always the beginning of your interval. So x sub 0 is the beginning of your interval, which for this problem is 0 because you're starting going from 0 to 3. And then I times delta x. Well, we just figured out delta x right here in purple. So we plug that in. Now, when you're looking at this, if you wanted, you could write it as either a 3 over an n times an I, or you could write it as a 3i over n. It would not make a difference. So we need to go ahead and use this, and then we'll have to take our limit of it. So basically, we got to look at what our function is. Well, your function is input squared. So it's going to be input squared, so your input's your x sub I, times delta x, which is the width of your rectangle. So we just figured out x sub I right here to be 3i over n, so we have to plug that in. So 3i over n, and then because it's function squared, we have to square the whole thing. Multiply it by your width, which is this purple 3 over n. So now all we're going to do is square the top and square the bottom, still with our 3 over n afterwards. Now we can just multiply the top, multiply the bottom, so we get 27I squared over n cubed. Now our variable that we're dealing with here is I. So we now have an I squared times something. Well, one of the rules says if you have your variable times something after your summation, you can pull that stuff out in front. So our 27 over n cubed we're going to pull in front, and then we just have the sum of I squared. Now, remember, we have a formula for the sum of I squared. We had two options. One, where it was one big fraction, if we knew the value of n. And then we had another option, which was separate fractions if we didn't know the value of n. And we don't know the value of n, so we're using the second fraction. So sum of I squared from our formulas would be this. Now, all we have to do is distribute through. So distribute through, distribute through, distribute through. When we do that, we would get this here. Now, that's the sum of all your rectangles. But remember, we said we were going to have our limit of the number of rectangles go towards infinity. So we're basically taking a look at the limit of this going towards infinity. Well, if we do that, when we do our limit here, we end up getting, well, n going to infinity has no effect on the 9. N going towards infinity would be 27 over something big, so that would be close to 0. And then we would have 9 over something big because n's going towards infinity. In other words, we would get 9 for our answer. So one last problem here. We still have our limit as we approach infinity of our sum. Here's our summation. We got to figure out x of I, what we're plugging into our function, and we got to figure out delta x. Delta x would be then 5 minus 1 divided by n. In other words, it's just 4 over n. Then we got to figure out x of I. X of I is x sub 0, which is always your beginning. In this case, it's 1. Plus delta x times I. Well, delta x was at 4 over n. So we could just write it like this. So now we need to come along, and instead of writing f of x of I, I'm going to write out my function, which is 100 minus 3 times input squared. So f of x of I is my function. My function was 100 minus 3 times input squared. So I'll go 100 minus 3. Instead of x of I, I'll plug in what x of I is, and then I have to square that. And then instead of writing delta x is 4 over n, I'll plug that in. Now I just need to do some algebra, simplify it down. So I'm going to go 1 plus 4i over n times another 1 plus 4i over n. Now I can distribute through my negative 3. Collect my like terms, which would give me a negative, or a 97, because 100 minus 3. Now we could go ahead and distribute in our 4 over n. 4 over n times each one of these gives us this here. Notice blue and red together make purple, so that's why we got the colors going this way. Now, this is really this blue fraction times 1. This is really times an I. This is times an I squared. So we're going to go ahead and apply our sum to each one of these. But since it is times a 1 here, times an I here, times an I squared here, These numbers we can pull in front. So our 388 over n we can pull in the front of sum of 1. Then over here we can pull our 96 over n squared in front of the sum of I. And then over here we can take our 192 over n cubed and pull it in front of our sum of an I squared. So you have a formula for the sum of 1, and that's n. So we'd have 388 over n times n, which you know is 388. Here we'd have our negative 96 over n squared, and then we have a formula for the sum of I, so we can plug that in. If we want now, we could now distribute through this, and we would get this here. We also have a 192 over n cubed times the sum of an I squared. Sum of I squared formula we could plug in here. We could then go ahead, distribute that through, and we would get this down here. Now, at this point, if you wanted to collect like terms, you could, but remember, we're looking at our limit as n goes towards infinity. There's no n here, so it has no effect on that. There's no n with our 48, has no effect on that. Here we have 48, it would over n, so it'd be 48 over something big, which is going to go to 0. There's no n here, has no effect on that. N's on the bottom, so your bottom's going to get big here, so these both go to 0. So we add and subtract all these together, we get 276.